So this is a question from the 2011 BC Calculus exam, and this is problem number 1 that did allow the use of a calculator. And what you have presented to you here is that a particle is moving in the xy plane. The position of the particle is going to be determined by a set of parametric equations. So the x coordinates determined by a function of t, the y coordinates also determined by a function of t, and those are not going to be given to us. But what we do have access to would be the rate of change of the x coordinate of position, the derivative of x, and also the derivative of y with respect to t. We're told here at the end of the problem statement that when t is 0, the x coordinate of the object's position is 0, and at that same time the y coordinate is -4. In part A, we want to find the speed of the particle at time t equals 3. Now, in physics, if you've ever found the speed of a particle that's moving two-dimensionally, what you typically would do is you'd have the x component of velocity, right? So maybe this vector has a magnitude of, say, 1 unit, and then you'd have the y component of velocity, so maybe this vector has a magnitude of 2 units. The speed would be the magnitude of this resultant vector. So the speed would be the value of the hypotenuse of this right triangle right here. So to find that, you would just use a little Pythagorean theorem, and we want to use a similar approach to find the speed of the object at t equals 3. The x component of velocity at t equals 3 is going to be the rate of change of the x coordinate of position, the derivative of position, evaluated at 3. Similarly, the y component of velocity at 3 is going to be this derivative evaluated at 3. So we're going to find the magnitude of the resultant vector. So these numbers, the 1 and the 2 that I threw over here, aren't the values for this specific particle, but you would be able to determine what the magnitude of this vector was with this. You'd be able to determine what the magnitude of this vector was with this. We're solving for c within the Pythagorean theorem here. And if you evaluate that on the calculator, what you end up with is you end up with 13.006. And then in the second part of part A, it wants us to find an acceleration vector. Now, in physics, what you would probably do is you'd probably find the x component of acceleration, the y component of acceleration, find the magnitude and the direction of that resultant vector. In calculus courses, what you typically do is you just list the vector component-wise, meaning it's almost going to look like an ordered pair. The second derivative of the x coordinate of position is going to be the x component of acceleration. The second derivative of the y component of position with respect to time is going to be the y component of acceleration. So if we do the derivative of this and evaluate it at 3, we're going to have the x component of acceleration. Similarly, the derivative of this evaluated at 3 is going to give us the y component of acceleration. This is something you can do on the calculator. Although we didn't really have to rely on the calculator for the derivative of this. Hopefully you look at this and say derivative of that's 4. There's not even a t to put 3 in place of in that derivative. And so at t equals 3, the derivative of dx dt is going to be equal to 4. And then if we want to know the derivative of dy dt at t equals 3, what we're going to be able to do on the calculator here, since we don't necessarily need the derivative, we just need the derivative evaluated at a given location. On the TI-83, you can find this option, the numerical value of a derivative in the math menu, and the call sequence would be type in the function you want the derivative of. Well, the function that we wanted the derivative of was sine of t squared, right? So I type in my function that I'm looking for the derivative of, comma, variable of differentiation. Now I put x into my calculator, so I did kind of swap the t for an x as I input this to the calculator. And then I want to give it another comma and tell it where I want to evaluate that at. And your answer, rounded to 3 decimal places, would look like this. And so the acceleration vector would be represented like that. You don't have to worry about finding the magnitude and the direction of that vector. In part B, we want to know the slope of the line tangent to the path of the particle at time t equals 3. So that would be the slope of the tangent line, and that would still, since we're moving in the xy plane, still be the rate of change of y with respect to x, evaluated at the t value of 3. And the way you're going to find that when your curve is defined parametrically is you're going to do dy dt evaluated at t equals 3 over dx dt evaluated at t equals 3. This is definitely something you can rely on the calculator to carry out for you. So put 3 here, put 3 there, make sure you do this over this, and you're going to get a value of 0.032. Part C wants us to find the position of the particle at time t equals 3. So what we start with is the initial x coordinate of the object's position, and that's 0. So the initial x coordinate is 0, and then I'm going to add to that how much the x coordinate has changed from 0 to 3 by integrating the rate of change of the x coordinate of the object, integrating the derivative of the x coordinate of the object with respect to time. And this is something you can definitely toss into the calculator, and then you get a value of 21 for the x coordinate of the object at t equals 3. Similarly, for the y coordinate, we're going to take the initial y value, which is -4, and we're going to add on to that how much the y coordinate of the object has changed between these two times by integrating the rate of change of the y coordinate of the object. And that's, again, something you can toss right into the calculator, and you get an answer of -3.226. So this would be the position of the object within the plane at t equals 3. Last piece of this question wanted us to find the total distance that this particle travels over the time frame from 0 to 3. Now, you've done problems that have dealt with motion in a single direction, motion along the x-axis, motion up and down. And if you had a velocity function for motion acting along a single line, to find the total distance traveled, what you've probably done is you've integrated the absolute value of velocity with respect to time across the limits of integration. This quantity right here is one way that we can define the speed of the object. The speed is defined to be the magnitude of the velocity vector, or the absolute value of the velocity. And so if we integrate speed from 0 to 3, we're going to have our result. We talked about speed a little bit in part A, and speed would just be involving finding the magnitude of the resultant vector, like we had back here with this triangle right here. It's just a little Pythagorean theorem. So our speed function, without specifying the t value that we're using, is going to look like this. If we integrate our speed function from 0 to 3, we're going to have determined how much the object travels along its curve over these limits of integration. And since this is a calculator question, we can definitely, now you have to be careful with your grouping symbols. You notice a whole mess of parentheses being used here. If you have a TI-84 Plus, you have a little bit nicer time inputting this to the calculator. But with the TI-83, just really watch your grouping symbols. But you can do this integral on the calculator, grab this out of the math menu, and integral is carried out on the TI-83 for us.